Hello, my name is Emily Johnson. My partner Ben Hahn and I have been working on the cost-effective do-it-yourself electrometer under the guidance of Dr. Damon Miller and the sponsorship of the Western Michigan University Neurobiology Engineering Lab. Thank you in advance for listening to our talk.
In order to understand the scope of our senior design project, it is important to understand what an electrometer is. These devices are the backbone of biological neural research because they are capable of providing nanoamp currents to neurons. The accuracy of these devices is incredibly important to researchers, as minuscule changes in current can have substantial effects on the neurons. Electrometers also record the resulting neuron voltage change, which is indeterminably small without the use of specialized equipment. Electrometers have long faced the problem of being financially unobtainable for many hobbyists and collegiate student laboratories, as commercial electrometers cost around $5,000 per instrument. This financial barrier has prevented many people from exploring neurobiology. However, a recent Western Michigan University master's student, Mr. Lucas Essenburg, designed and built an electrometer for around $200. This proved that quality electrometers could be built for a price that is affordable for many laboratories.
The motivation behind this project is to develop an affordable and educational do-it-yourself electrometer kit marketable to high schools, universities, and hobbyists. The kit must include all parts for construction and detailed documentation. Our objective was to create an electrometer kit that includes 3 printed circuit boards entitled Head Stage, Main Stage, and Power Supply, one enclosure that fits any standard electrophysiology test rack containing both the main stage and the power supply, a head stage that will be placed within a thinner, compact enclosure that can be mounted on a micromanipulator, and an instruction manual detailing the function and construction of the kit.
The physical specifications for this project strongly revolve around ease of kit assembly and construction. We decided that all resistors and capacitors must be standard values. Furthermore, all of our components had to either be through-hole or have a through-hole adapter to work with the printed circuit boards. The size of the head stage had to be reduced to be easier to use in laboratory. Furthermore, the noise of the device had to be small enough as to not interfere with the function of the electrometer. In regards to the printed circuit boards, the high voltage traces of our final designs had to be at least 3/4 of a millimeter thick, and the final designs had to be placed in Gerber files for future ordering. In regards to the functionality of our project, our electrometer had to be able to work similarly to that of a commercial grade device. The whole list of specifications is on the video, but as a summary, our electrometer must have a bridge balance, capacitance neutralization circuitry, a DC offset, and current monitoring circuitry.
Let's talk about our constraints. Economically, we want to stay close within Mr. Esenberg's original estimate of $250. The kit should sustain for at least 10 years with high quality components. For manufacturability, the printed circuit boards must be designed in KiCad in case of future revisions. KiCad is an open source tool available to anyone. All files used in the design should be readily available and easy to access. Since the kit has such small signals, a noise analysis must be completed to minimize any contributions of various components, and we need to remove any excess op amps. As has been stated before, the design can be split into 3 sections: AC to DC power supply, the main stage, and the head stage. The AC to DC power supply transforms the AC voltage down to a plus or minus 5 volts to power our components. The main stage contains most of the calibration circuitry. Recall that this device is measuring the voltage drop between the electrode and the neuron bath. As data collectors, we only want the voltage drop between the cell and the bath. To accomplish this, we need to null the resistance of the electrode using the bridge balance, and then update the DC voltage using the DC balance as necessary to receive the clearest picture of our output signal. The tickle signal is a pulse sent through the electrode to wiggle the tip of it. During experimentation, this is used to remove excess waste from the electrode and help puncture the cell membrane. The main stage will also include any connections to external scopes and data capturing devices. Lastly, the head stage contains the capacitance compensation, the nanoamp current converter, and the electrode. The circuitry within the head stage is very sensitive, so it is vital to have the circuitry as close as possible to the experimentation. One of the main goals for this project in the fall was to optimize Mr. Esenburg's original design. Using LT-Spice, Ben and I were able to calculate the noise across the nanoamp converter, current monitor, bridge balance, DC offset, and capacitance compensation circuitry from 1 Hz to 100 MHz. At 14.375 millivolts, this may be less than ideal, but upon further investigation, we found that a crucial component within the nanoamp converter was the creating majority of the noise. Thus, no action was taken to lower it.
The main focus of this project was the development and creation of printed circuit boards. For this, we ultimately decided to use KiCad. This program is free to use, which will allow future individuals to work and improve our project for free. Another major pull towards this program was its large library of footprints and the fact that it is very intuitive to use. The next few slides will detail the design of our printed circuit boards and the changes that we have made to them. The main stage of the device contains the majority of the circuitry for the electrometer, including the DC offset, the bridge balance, the current monitor, and the tickle signal. The main stage also serves as the connector between the power supply and head stage, and has connectors for those printed circuit boards. The picture on the left is the actual printed circuit board that we ordered, while the picture on the right is a screenshot of the layout from KiCad. This board is divided into sections to improve visibility of the circuitry for possible troubleshooting. Up next is the printed circuit board for the head stage. This board contains both the capacitance compensation and the nanoamp voltage to current converter. This circuitry is the most vital part of the electrometer, as it is the way to accurately provide the nanoamp current to the neurons. This board was particularly difficult to design. First, the board had to be small in order to meet our physical specifications. Secondly, we had to minimize the electrical losses from the traces, which meant that the traces had to be as short as possible. Therefore, a number of different orientations had to be attempted to both decrease the size of the board and the length of the traces. As with the main stage, the left picture is the physical board that we ordered, while the KiCad layout is shown on the right. The last printed circuit board to show you is for the power supply. The power supply takes the 120 volt AC power supply from most electrical engineering laboratories and converts it into a positive 5 volt supply, a negative 5-volt supply, and a ground level via a transformer and regulators. This power supply has a relatively low level of noise, thanks to large capacitors placed between the regulators and ground. The biggest difficulty of designing this board was creating the footprint for the transformer. Footprints serve as the way for KiCad to know the shape of a device, how many pins a device has, where each pin is located on the device, and how big the holes in the printed circuit board need to be to accommodate the pins. The only major difference between this board and the boards for both the head stage and the main stage was that this board was the only 2-layer board designed. Both of the other boards utilized 4-layer board designs to create a ground plane as well as both a positive and a negative 5-volt planes. After purchasing and reviewing our printed circuit boards, we realized a couple of changes that needed to be made. First, we wanted to increase the size of all of our pads. This would make soldering easier without sacrificing any functionality. Next, we adjusted the size of some of the holes, as the pins for some of our components were either too big or too small for the holes that we originally designed. We also redrew some traces that we noticed were too close to some pins or other traces. Finally, we updated our silkscreen to improve the visibility of some of our traces.
The main stage and power supply will be enclosed together in one 8.5 by 10 by 5.25 inch box, which is half the size of a standard electrophysiology rack. This will allow customers to place 2 electrometers or 1 electrometer and additional hardware in one rack.
The budget for our electrometer kit came out to be around $375. As you can see, this is higher than we both anticipated and desired. The main reason for going over budget was the cost of the printed circuit boards. We also did not get a firm price for the enclosures, as we did not order them prior to the stay-at-home order, although we do believe that they will only cost around $40. To understand the cost of each electrical component, we would like to refer you to Mr. Esenburg's thesis. Although some components differed from his thesis, our design used many of the same components, and the major cost discrepancy between our budget and his budget comes from his inclusion of his enclosures within his budget. Although we did end up over budget, we do still deem this project to be successful. We do believe that we met the goal of creating an affordable electrometer kit. For less than 10% of the standard price of commercial electrometers, colleges and hobbyists are able to purchase quality electrometers that expose people to biological neural research. Furthermore, depending on the demand of this product, we do believe that costs can decrease, as larger quantities of parts generally result in decreased costs.
During this year, Ben and I were able to reduce the number of op-amps in Mr. Essenburg's original design, perform a noise analysis on the circuit, design all 3 printed circuit boards within KiCad, order and receive all components and boards, make slight improvements to the PCB files to increase ease of use, and design both housing units within AutoCAD. However, due to the COVID-19 outbreak and the stay-at-home order issued by Governor Whitmer, we were unable to assemble and therefore test a working prototype of the electrometer. Although started, the manual detailing both construction of the electrometer as well as troubleshooting issues was not completed. Therefore, the project is only roughly 70% completed. .
The next steps of this project include many of the steps we were unable to finish this semester due to the stay-at-home order. The first step would be to purchase the 2 enclosures. Then, a working prototype should be constructed using the printed circuit boards, enclosures, and electrical components that we ordered. This prototype will then need to be tested. This will likely occur with Dr. Jellies in his laboratory. Any updates that need to be made to either the printed circuit boards or the enclosure designs should then be made. Finally, a manual should be written that explains the function of an electrometer, the construction of our electrometer, and fixes to potential problems. We envision this manual to be similar to the manuals of the old Heath kits. Before we finish, we would like to thank a few people for their support and contributions to this project. First is Dr. Damon Miller, who served as the advisor for our senior design project. His support and knowledge helped us thrive. We would also like to thank the Western Michigan University Neurobiology Engineering Laboratory for sponsoring our project. Next, we would like to thank Mr. Donovan Squires for providing some key insight into our printed circuit board designs, as well as a number of ideas that helped us improve our boards. We would also like to thank Mr. Lucas Essenburg for helping us understand his thesis, as well as providing us a number of documents and files that we used throughout this project. Finally, we would like to thank Dr. John Jellies for offering his laboratory to us to test our device, as well as teaching us about neurobiology. Finally, for those interested in Mr. Esenberg's thesis, we highly recommend that you spend some time reading it, as it helped us immensely on this project.